Section 7.3 Trigonometric Substitutions. So this is in the book they have used three types of trigonometric substitutions. We will discuss only two types here. Now recall from chapter 5 that the definite integral, something like this, we evaluated by using geometry because this gives us area between the half circle or semicircle above the x-axis, and it is bounded below by the x-axis. So if you have a semicircle, with radius 3, and then this integral basically just gives the area from -3 to 3, and so which is half of the area of the circle with radius 3, which means half pi into 3 square or 9 pi over 2. In the same way, if we are looking at this integral, this is the quarter circle, so from 0 to 3, so it will be just this portion, so which will be 1/4 of the area of the circle. So these integrals we were able to evaluate by using geometry, but often we can encounter integrals which look something like this or like that. Now these are, if you note, these are still the equation of the semicircle with radius 3, but now we are talking about area from -2 to 2. So imagine that we are looking at something like this. So we have our semicircle, but now instead of going from -3 to 3, we are somewhere here and we want this area. So how do we evaluate these? And this is cannot be done by using geometry, so we need calculus for this. And for that we need trig substitution. So what are those trig substitution? Basically it says whenever you have an expression of this kind where you have a square root and under the square root you have the quantity a squared minus x squared, then you will use this substitution, which is what we call the trig substitution. So we are substituting a, converting it into the x into the theta, the new variable theta. So we take the substitution x is equal to a sine theta. So note a is the square root of the quantity over here. So if in your example you have 3 minus x squared, remember a squared is 3, so a will be square root of 3. So we'll take the positive values here. So this is how you will be substituting, and then we will be using the identity 1 minus sine square theta equals cosine square theta for the first case. And note here that the theta is restricted between these values because we will be using the inverse function of theta as well, because from here you can see the sine of theta is equal to x over a, and the theta will be equal to sine inverse of x over a. So that's why we have to restrict the theta between minus pi over 2 and pi over 2. The second case is when you have a quantity a squared plus x squared under the square root. So for example, if you want to evaluate an integral like this, 9 plus x squared dx, then you will be using the substitution x is equal to a tangent theta. Note here, you cannot use the substitution u equals 9 plus x square here because that won't help you, and that's why we use, in these special cases, we use the trig substitution. And again, theta is restricted between -pi over 2 and pi over 2, and the identity that we will be using is 1 plus tangent square theta equals secant square theta. Note here, in the case of the tangent substitution, we don't have the equal to sign in the interval, and the reason is that the negative pi over 2 and pi over 2 are vertical asymptotes of the theta, of the tangent theta. And so from here you can see that tangent of theta is equal to x over a. So theta will be equal to tangent inverse of x over a. So these are the values that we will need when we solve these integrals. So let us look at first example. If we have 1 over square root of a squared minus x squared. Now recall that if we have 1 over square root of 1 minus x squared dx, then the integral is sine inverse of x. But now instead of 1 we have a squared. So how will we find the integral of this quantity? Well, we make that substitution, that x is equal to a sine theta. So this gives us dx is equal to a cosine theta d theta. And so we substitute and we end up getting 1 over so we get integral 1 over square root of a squared minus, now note here, be careful, you have to square the whole quantity a sine theta. You have to square this whole quantity. So you get a squared sine squared theta. And then a cosine of theta d theta, which gives us a cosine theta on the top, and at the bottom what we do is we factor out the a squared, and then inside we are left with 1 minus sine squared theta. Now this a can be pulled out, and we know that 1 minus sine squared theta is cosine squared theta, so that we end up getting a cosine theta over a times square root of cosine squared theta d theta. But note here, this will just be cosine of theta and they will cancel out. So a and a cancels, right? So let me rewrite it, cosine of theta over cosine of theta, so that we end up getting d theta. So that this is going to be just theta plus c. So, but what is theta? We wrote up there, theta is sine inverse of x over a. So that is the difference here. In this case, we had just sine inverse x, but when we have a squared minus x squared, then we get sine inverse x over a plus c. Okay, so looking at this next example, again recall that if we have 1 over 1 plus x squared dx, the answer is tangent inverse of x plus c. And now we have 1 over a squared plus x squared dx. So we start by making our substitution. Let x is equal to a tangent of theta. Then dx will be equal to a secant squared theta d theta. Going back, substituting, we get 1 over a square plus a square tangent squared theta times a secant squared theta d theta. Factoring out the a square from the bottom, but using the identity that 1 plus tangent squared theta equals secant squared theta, so we end up getting 1 over a secant squared theta over secant squared theta d theta. But theta and theta, secant squared theta cancel out, and we are left with 1 over a integral of d theta, which is going to give us 1 over a theta plus c. But what is theta here? Well, you have to go back to your substitution. think of what the substitution was. X is equal to a sine theta, a tangent theta. So that tangent of theta is x over a. So that theta is tangent inverse of x over a. So go back, substitute. So we have 1 over a tangent inverse of x over a plus c. So the difference now here, in the previous case we didn't get a 1 over a in the front, but now we have a 1 over a in the front. So this is how you will be doing the trig substitutions. Looking at another example here, we have integral of square root of 16 plus x square. So again, notice in this problem, you cannot do the use substitution 16 plus x square because we do not see the derivative of this interior being multiplied outside. So this substitution is not going to help us. So we need to do the trig substitution here. So we say let x equals, so a square is 16, so that a will be 4. So let x is equal to 4 tangent of theta. Then dx will be equal to 4 secant square theta d theta. I'm coming here, substituting. So we get 16 plus 16 tangent square theta times 4 secant square theta d theta. So notice here, this quantity here, this gives you 4 secant theta. You should be able to figure that out. So that this becomes 16 secant cube theta d theta. So we already learned how to integrate secant cube theta. So we will do that. So remember, secant cube theta d theta, we do it by the integration by parts. We write it as secant of theta into secant square theta d theta, and we say let u equals secant of theta dv equals secant square theta d theta. So du is secant theta into tangent theta, and v is just tangent theta. So that this quantity becomes uv. U is secant theta and v is tangent theta. So secant theta into tangent theta minus integral of v du. V is tangent of theta and du is this whole quantity. So you can see this gives me secant theta times tangent square theta d theta. Using the identity or the Pythagorean identity again. So we have tangent square theta is secant square theta minus 1, which is so remember what we do here now, because our left hand side was secant cube theta d theta. So we will move this over, so we end up getting 2, and then we will divide by 2. So I'm going to do those two steps together. So eventually we end up getting that secant cube theta d theta is equal to 1/2 secant theta tangent theta minus plus 1/2 ln of secant theta plus tangent theta, which is the integral of this quantity. Therefore, your answer will be, we have to go back into now x. So how do we do that? Well, there are two ways you can do it, using the identities, or you can use the triangle method. So you can use the fact that substitution gives us x is equal to 4 tangent theta, which means tangent of theta is equal to x over 4. So tangent theta is x over 4, which gives us x over 4, so that this side will become 16 plus x squared. And now we just substitute. So our integral 16 plus x squared dx will be equal to, remember it was 16 into this quantity, so it will be 16 into 1/2 into secant theta. Secant theta will be square root of 16 plus x square over 4 times tangent theta, which is x over 4, plus 16 into 1/2 into ln of absolute value of 16 plus x square over 4 plus x over 4. Simplify and we end up getting x into square root of 16 plus x squared over 2 plus 8 into ln of 16 plus x squared plus x whole divided by 4, or 4 could be used in the constant, so we can just say this is plus c. Okay, let's do another video for this example.